Hey everybody, so today I'm going to be showing you a couple of videos on linearization of graphs. The first video, which I'm going to make right now, is going to look at, given some data, how do we use that data to graph? And then what do we do with that graph? How can we manipulate the data in such a way that we can get a linear graph, which number one gives us a constant slope, which could help us with various things in the future. And it also verifies the relationship between the two variables. Is it a linear relationship, quadratic relationship, inverse relationship, right? And so that's the first goal. We're going to do two examples of that in this video. Okay, if you're more interested in the questions that are more AP style, which is they give you a situation, you come up with a relationship, and then figure out what you need to do with the data without graphing it, that will be in my next video. Okay, so hopefully if you choose the one that will be helpful for you. So let's go ahead and start with this one. So we've got some data here. It's just a ball rolling down a ramp. Okay, we're going to just start. It asks right away, question number one, which variable is independent and which is dependent? Well, we're measuring for a certain amount of time. Generally speaking, time is going to be our independent variable, right? It's very difficult for time to depend on something else. In this specific situation, we're letting it roll for a second and figuring out how much distance is achieved in that amount of time. So time is going to be our independent, which is x, and then the distance is going to be the dependent, which is y. Okay, so we label the graph, we put that in, and then we're going to put the data values into the graph. Now I'm going to do that all at once. I'm going to talk really quick about this number 3. Make sure you use values such that you'll use most of the graph. You'll see my graph's already labeled here, but the time goes from 1 up to 6 seconds. So I want to make sure that when I put that data in, that on my graph, 1 to 6 covers most of the graph, right? I don't want to make my graph go from 1 to 20 because 1 to 6 would only be like the first third, first quarter of my graph, and that doesn't lend to a very nice graph. It makes it more difficult for us to see relationships. It also makes it harder for us to create linear graphs and get slopes and other things from it later. It makes it less precise. All right, so we want to make sure that we cover most of the graph. You'll also notice that distance goes from 3 up to 58, and on my y-axis there, it goes 0, 10, 20, 30, it goes up to 60, which will fit that distance without having too much extra there. All right, so I'm going to go ahead and pause it at this point. We'll go ahead and throw in, we'll just kind of speed up this section. We'll put all the data points in, label each of the axes, and then we'll move on with the question. All right, so we did 2, 3, and 4 right there. We got all the data points in. I'm actually going to add in one more data point, which you don't see there right now, and it's actually not in the data, but we're going to assume that at 0 time, my ball has traveled 0 centimeters. All right, so we've got our data on here. One of the things that I want to mention is, you know, some students worry, well, you know, how do I know exactly where 7 centimeters is? You know what, it doesn't matter. If somebody looking at the graph would look at that and say, oh, that's about 7, then it's fine, right? You're dealing with things that are not super precise and accurate anyway, so we're going to deal with what we've got. You know, if you put it into a computer program, yeah, it'll put it in exactly the right place and it'll find all the values that you need. But we're not doing that. We're trying to learn how to graph and how to analyze a graph. And so just be as accurate as you can. All right. Okay, in number 5, it actually says to identify the function type by looking at the graph. And I think by looking at that, it's pretty clear that it's not linear, okay? Our best guess probably at this point, because of the curve upwards, is that it's a quadratic, all right? So I'm going to say that it's probably a quadratic. That's number 5 here. And then I'm going to go on to number 6, which says draw a line of best fit. And when it says line of best fit, I know you learned in algebra and geometry the line is a straight line that connects 2 points, blah, 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 that goes on forever and ever in both directions. Okay, in this class, if it says line, it's just a line, okay? Now, you do have to make sure, especially in AP, that you're not doing all sorts of coloring and making it really thick. They just want you to sketch in one simple, single, straight line. not straight line, one simple clean line. So that's what I'm going to draw in here right now. And you can see, here we go, pretty clean there, going through most of the points. It doesn't actually have to go through all the points. Sometimes your graph won't hit every single point, and that's all right. It's more important that you represent the relationship that we believe is what's happening here, which is a nice kind of quadratic half of a parabola going on there, okay? Step number 7 asks us to linearize the data by changing the values on the x-axis. Okay. Now we learned, you know, that a quadratic is represented by y equals x squared. And so hopefully, if we are to square the x values, remember the whole point of this is to get it into kind of a y equals mx plus b format. You can see that there's no b over on the end. There's no y-intercept. The y-intercept is 0 there. Okay, so that's fine the way that it is. Instead of graphing x, we're going to graph x squared. We want that to be the variable, okay? And so what we're going to do is we're going to go back to our original data and we're going to square each of the x values, okay? So this 1 is going to stay 1. The 2 is going to become 4. And of course it's 0.0. I'm not going to worry too much about that because I can't graph that accurately on the graph anyway. The 3 is going to become 9. The 4 is going to become 16. The 5 is going to be 25, and the 6 is going to be 36. So what I've done now is I've changed the x-axis to represent x squared, or time squared. All right? And so now we're going to actually put that data into our graph. So we're going to scoot this up just a little bit, okay, so that it fits in our screen. There we go. Now, one of the things we want to do is, again, we want to make sure that it actually fits inside of our graph here, right? And so I see that the x values now go all the way from 1 up to 36. So I got to make sure that I can fit up to 36 on my graph. And it looks like if I just go by ones down there, right? If the left-hand side is 0, 1, 2, 3, 4, 5, 6. If I just go by 6s, 6, 12, 18, 24, 30, 36, right? I can fit on there. And that's probably the easiest way to do it. I don't want to go by, you know, quarters or 3/4 or anything weird like that. We'll stick with this. This will fit. Most of the graph will be filled up by our data. The y doesn't really need to change, right? I didn't change the y at all. So I'm going to leave the y as 10, 20, 30, 40, 50, and 60. Okay, the y-axis is still going to be distance in centimeters. And the x-axis is now time squared, okay, which is in seconds squared. Okay, and that's important because we have actually changed what's on the x-axis here. All right, so we'll go ahead and we'll take our new data and we'll put that into the graph now. All right, now we look at that data and what do we see? We see a pretty darn good straight line, don't we? We linearized the data by recognizing the relationship was quadratic, graphing it with a quadratic x value instead of a linear, and it's now in a linear format, y equals mx plus b, where x is time squared. All right, so now we're going to go ahead and draw in our line of best fit. Please do use something straight to draw these in. There's really no reason not to. Okay, but we got a nice straight line there. It should be straight because we just linearized it. Now, number 8 says, describe how your analysis supports the function type identified in 5. Well, because I did the quadratic linearization process, I squared the x's, and when I graphed it, it gives me a linear graph. That confirms or supports or verifies the original relationship being a quadratic relationship, okay? If I were to do this and graph it and not get a straight line, then it would not verify that relationship. It would mean it's something else, maybe a cubic or something else, right? And so we'd have to try a different process. So this confirms the fact that it is a quadratic graph, okay? Next, it goes on to find the equation of the linearized graph. Okay, you should be able to do this. I feel like hopefully if you're in AP Physics to this point, you're able to find the slope and y-intercept of a linear graph. I'm going to go ahead. What I would suggest is make sure that you pick points that are far apart. They do need to be points on the line. So I'm going to choose this point right here, which is 0, 0. It doesn't actually have to be a data point, right? For example, I could say, I like this point right here, because that point right there looks like it's at exactly 2440, right? That's not one of the original data points, but it is on the line. The only thing that you need to be careful of is make sure that the points are at least 50% of the graph apart from each other. Okay, that's important because that will help to minimize our uncertainty. Okay, the closer the points are together, the more likely that our line or our slope could be off in that area. Okay, so I'm going to go ahead. So that means my slope is 40 over 24, which of course those are both divisible by 8. So that would be 5 over 3. So I now have my equation, which will be y equals 5 over 3x plus 0. But remember that x here is actually times squared. And so I can rewrite this so that y is distance, which is equal to 5/3 times time squared. All right, and that's essentially what we just did. And so now we have an equation that we could actually put that original data into, and it should give me something really close to what we just got. All right, so that's our first example. Let's go ahead, we'll move on to another one.